Welcome, everyone, to the ESTeem wireless training class. My name is Eric Marsky, and for the next few days, we're going to take a look at how a radio functions, primarily the equipment that we manufacture. We're going to take a look at quite a bit of different topics, from the basics of radio to RF design, the steps that are required to actually make a reliable wireless solution. And the purpose behind this, more or less, is not to get anybody expert within 2 days, but to get a familiarity with the terminology that's used, how some of these items are actually come together. And you'll find as we go through this that a lot of the common questions you may have had about wireless will come up. They are common subjects, so I think the best place to start really is just an overall introduction to who we are and what we do. A Steam wireless modem is actually known by the corporate name of Electronic Systems Technology. Okay, Electronic Systems Technology is actually a publicly held company. It was incorporated back in 1982. The first public offering was in 1984, so we're over 35 years of manufacture. The big thing to understand is that radio is all that we do. We do not do this as a side project, as an additional type of equipment. Wireless communication is the only type of radio communication that we offer. Because of that, we need to understand that wireless has been around for quite some time. We actually had the first wireless modem was type accept back in 1985. We actually hold the patent on the wireless modem since 1987. Most people knew us by the product name of ESTeem, and because of that, we actually are doing business as ESTeem wireless modems, and that's commonly what you'll see listed. Even under our website name, ESTeem.com, most people understand that. That's why we're doing business that way. To date, we can still track well over 45,000 plus ESTeem products in service worldwide today. Both our corporate offices and the production facility is actually located in Eastern Washington in a city called Kennewick. Now, just to give you an idea of some of the major markets that we work with, is we actually handle many different types of applications. We do communication for water, wastewater, mining applications, oil and gas, material handling, power, energy, factory floor automation, agriculture, and we'll just call it Ethernet networking. Now, each one of these has some specific elements to it, and we will cover those here in our next section of some of the ways that wireless communication solves many of these needs. You're going to find some very common elements to this communication, something that's very long range or very difficult to get to. But you'll see that no matter which market we're going into, which one we're actually covering, we're really in the business of replacing cables. So that's why we get into many different applications. We can go just about anywhere. We've done everything from hard industry to the entertainment industry for, say, Universal Studios, to power, to both distribution and supply. There's many different ways that it goes into, and that's why it's so diverse, the different markets that we go into. So you'll see here as we go through these different slides and availability, hopefully something that will look into your next application that you're looking into. To give kind of an overview of the class and some of the broad subject matter that we're going to be covering, we're first going to start out with the general radio overview. And the idea behind this is so that we can all talk a common language. There are a few terminology that's used in radio that unfortunately becomes a series of buzzwords that you've probably heard, but now we're going to actually define those so that we can all talk a very common language. That's probably going to cover us through the first day, because beyond that, we're also going to take a look at antennas. Strangely enough, that you're going to find out that most of the changes that we make inside of a wireless system really come back to the antennas and the cables. And we'll see why that is so important to understand. The next thing we're going to take a look at, and this will actually be a couple different training classes, is the actual RF system design. Because what we do is RF system design is actually 3 stages. We start out with a math modeled analysis. Then we perform an on-site confirmation, an on-site site survey, where we actually physically go to the site, take the test measurements with the equipment that we'll be using. And then we finish that up with what's called a commissioning phase, to where after the equipment is installed, you go back and perform those exact same tests that we did during the site survey testing. The idea being that the results that we should have during the commissioning should be somewhat better, if not the same, than we got during the site survey testing. Now, this may seem like a tremendous amount of work to go and do, but we need to understand what we're building here. The wireless communication is actually the backhaul. It is the infrastructure for all the other devices that get put onto it. So if we have a poor communication link somewhere on the network, every device that's connected to that communication link will have a poor operation. So this has to be the most reliable that we can possibly make it. So the RF design, like I said, is a couple different phases. And because of that, we're going to break this training class into a couple different classes. The first one being the math model analysis, our software that we've put together called the RF design program. And then the next day, we're going to take a look at what are the testing that we performed when we do the site survey. And ultimately, what do we do when we come back and do the commissioning? So we'll review those. Again, we're not trying to make anybody an expert within a couple days, but what we're trying to do is give people an overview of what's actually involved in that. Because most people are familiar with wireless. You know, we deal with wireless on a daily basis. Cell phones, Wi-Fi in your house, but very few people have a really good working understanding of what's going on there. So what we want to do is we kind of want to start breaking down some of these barriers. Then we're going to take a look at the radios themselves. In other words, our wireless products and how we fit into this larger wireless world. Then we'll get into the specifics of basically the Ethernet programming, to where we're going to take a look at where we fall in this Ethernet stack. What does this wireless communication actually solve? Where do we actually get in the data from? And ultimately, how do we get it from point A to point B? Because of that, then there are many different modes of operation. That section will also be broken into a couple different training classes. Then we'll take a look at the advanced programming of the radio. We'll take a look at the software utilities that we use to produce those. Then we'll go into more specifics of different series of radios, first with the Model 195 narrowband, and then with the 210 series. Those will actually be covered on the same day. They're fairly small as far as category when we take a look at the larger scheme of it. And then from there, we're going to take a look at some of the key elements as far as installation and troubleshooting. All right. And the first step we're going to do is these are kind of the breakdown of the individual elements, or these are the individual classes that we're going through. So you'll see it pop up here on the screen every once in a while. And what I'm doing here, you're probably not seeing my mouse move, but what I'm going to do is I'm actually just going to select the first one up here, which is the general radio overview. We're going to take a look again primarily to go over some of the terminology that is used in radio communication. Is its own, its own methodology, and because of that, we tend to assume that people really understand a lot of the buzzwords that we're using. But what we want to do is we want to get to a common language so that everybody can kind of understand this. We're going to break it down into hopefully it's as simple element as we possibly can. The first thing we need to understand is that wireless communication, it's not really new. As we saw before, we've been making radios for well over 30 years. So wireless communication, and especially when talking about data communication, it is not a new technology. But what it has done, it's changed dramatically over time as what the capabilities of that wireless communication are, the modulation types, and ultimately the solutions that it can provide. To give you an idea, the first generation of radios that came out was actually for serial communications. And the reason I say that when I'm talking about serial communications is we're talking about the interface of both the computer or the industrial controller. The first generation of serial, it was basically a very slow speed, direct interface between one device to the next. The first generation was just simply done with a frequency shift keying. The modulation type could really support about 2400 bits per second. Now, keeping in mind the first modems that came out were about that same, as far as dial-up modems, were about that same speed. So that was right in line with what it was. To give you an idea of what we're talking about as far as basically the latest hardware, most of those now are somewhere around 1900 to anywhere to 56 kilobits per second. Now, these are still not massive speeds, but they work very, very well for serial communications. What has dramatically changed the world of wireless is this terminology that gets thrown out there called spread spectrum. Okay, well, spread spectrum actually has been around for a very long time also, and we'll cover that here in a couple more slides. But the idea behind this is it utilized a technology that was actually originally a military anti-jamming technology and has been basically reappropriated for civilian use to use it for very high throughput communications. So what this has done is this allowed us to take us from kilobits per second and move us towards megabits per second. So instead of thousands of bits per second, we're actually moving millions of bits per second from point A to point B. So we've moved dramatically, just folds in scale into the future with the ability of spread spectrum. Okay. What spread spectrum ultimately allowed us to do is realistically put together what we call wireless Ethernet or a wireless LAN. Now, as honestly, the latest generations are getting to wired speed, if not faster than wired speed. And the best part that came about with wireless LAN is the IEEE, who actually is the industrial electrical engineering who puts together the standards for electrical engineering. They saw that they recognized that this is going to be kind of the future. And because of that, they actually took up quite a few and developed quite a few standards, which that's why you see listed there as open protocol standards, so that different manufacturers, you're not going or you're not locked in to one manufacturer from one device to the next. As you can imagine, if we had that in our home communication, that, you know, whoever has a Samsung or an Apple or something like this, if you had to go and get that, you know, made it up access point that only allows the communication for that device, how bad this would be. So what they've done is they set the rules, therefore that really opened up wireless communication as a good possibility. Okay, so to give you an idea of really what we're talking about in wireless, you know, we use this terminology a lot, but what does it actually do? Where are its best value? First thing we need to understand is wireless makes a lot of sense in the first one because that's where we use it ourselves. We use it in mobile communications, whether we're talking about a moving piece of industrial hardware, a device that's running on the factory floor, maintenance vehicles, overhead cranes. Use it a lot in public safety, to where they've brought, of course, they all have communication terminals and laptops inside of there for running wants and warrants and prints and, you know, license plates, things like this. All of that availability now is at the fingertips, but it's available because we've uncoupled our computer from a wired connection. Okay, same as happened in industrial control. And that's really one of the key uses of this, because there really are other methods of getting this communication, but they become very expensive. And quite honestly, they tend to be a little bit more fragile as far as communication. So wireless has really come into its own primarily in mobile applications. Makes perfect sense. The next one will be in what we just call it inaccessible areas. Now, what I mean by this may be simply across a parking lot where you need to get data from one side, so you've got a remote camera at the opposite side of a parking lot. So you need to get that communication back to a facility. Well, what are your options? You're either going to trench up and tear up your parking lot, or you're going to be going through some other type of means. Well, wireless makes a pretty good solution for that. Or it's just too difficult or too costly for cable runs. The next thing, it may be across water, across a waterway. A good example of this, just to give you an idea, is across airfield lighting. Okay, you see those little boxes as you're inside of an airport that they control the lights that turn on and off the terminal. Well, we've done a lot of different airfield lighting communication systems. Now we are essentially a backup for those. They actually run a couple different fiber networks, and we end up being a backup to those. But it is a perfect idea of where inaccessibility would come from, because it's just not something that you're going to go tear up, you know, lighting runways to get communication next time you need it there. A really good example is a long distance communication. Okay, now long distance, whether we're talking across a city, across a county, really it just becomes impractical or too expensive to run cable to it. Good example of that, and quite honestly, a lot of our applications come into water or wastewater, water distribution or wastewater systems, because they encompass, quite honestly, many of the different things that we've talked about. Not only long-range communication out to remote sites, but also they incorporate inaccessible areas and mobile applications. So it is a very good fit for that. But as you can see, radio is never going to completely replace all cabled communications. It's just going to fit these needs to where it's really, quite honestly, impractical to do it anyway. It's what they call the last mile communication. It's usually that piece that can really be solved and no other means necessary. Radio will solve those communication things. Okay. So how do we do this? Okay. We keep talking about this spread spectrum. What are we actually talking about here? Well, to be honest with you, spread spectrum actually has kind of an interesting history. It was actually developed back in World War II. It was actually the original technique was developed by an actress at the time called Hedy Lamarr. She actually was, her father and herself were actually physicists that actually came over from Germany to the U.S., but at the time it was not really, quite honestly, very good for an acting career to be known that you do physics and development in the spare time. But it was originally done for communication rates to steer correct torpedoes in World War II. Well, it developed throughout time. It was primarily kept as a military secret. And the military primarily used to, think of it as an anti-jamming technique. Well, if you're not familiar with what jamming actually means, is that if you are transmitting your information on a particular frequency, well, if somebody else transmits on that same frequency with noise, they're going to knock you off of that, so your information doesn't go through. That is a very back and forth game that has been played ever since radio has been used for military applications. So the idea behind this is that if you take a block of data and you send that same data on 10 different frequencies, the chances of somebody being able to jam all of those is very, very small. Okay. So what changed is that the civilian population, or this was actually allowed by the FCC, or the Federal Communications Commission, back in the early 90s. It was transferred over to a civilian type of modulation. What was unique there is that instead of using those 10 blocks of data to basically send the same information to make sure it doesn't get jammed, they use that 10 blocks of data to send 10 different data blocks. So now what you're actually doing is you're utilizing this wideband technology to go faster and faster communication. People have used it for many, many years and might not necessarily realize that the first cordless phones actually use spread spectrum technology. You've used it almost your entire life and probably didn't realize it. But the idea behind this is that's what has been the massive technology advance that quite honestly gets us everything that we are comfortable with as far as wireless goes now. Wi-Fi uses spread spectrum technology. Everything around that uses spread spectrum technology. So what are some of the terminology that is used there? Well, quite honestly, spread spectrum is kind of a broad category. What it really means is you can kind of break it down into many different techniques. The first technique that came out, which is what's called frequency hopping. Now, the easiest way to look at this is if you've got a block of data and you were to basically cut that block of data up into small little pieces, then what you're going to do is you're going to take each of those blocks of data and send it across this spectrum, whichever spectrum you're going to be using, and each block of data now comes across at different times. So if you're to line them up, say 1 through 10, it may transmit 1 and then 8 and then 3 and then 2. And the idea behind this is this pattern that it establishes is very difficult or very resilient to noise, background noise, and quite honestly, other transmitters in that same area, because the chances of you transmitting on the same frequency at the same time is very, very small. So the idea behind this is the difficulty in that, where is you not necessarily utilizing the type of modulation, because each one of those little blocks of data is not modulated much different than any other narrowband or a single transmitter. But what is different is that the receiver must be able to hop in that exact same pattern to get all that data lined back up again so that it gets through what we originally transmitted. Okay. Now, as kind of a opposite of that was the first generation of wireless LAN that came out uses a method called direct sequencing. Well, instead of taking that data and breaking it into small pieces, what it actually did is it mixed that data with a combining frequency. The resultant frequency, if you were to look at it on, say, a spectrum analyzer, we'll cover more about what that actually is here in a bit, so just bear with me. If you were to look at that on a meter, what it would look like is a very wide transmission, but a very low output power. Because really what you're doing is you're spreading all the data across this wide band. Well, the point behind this is that it worked, it was very resilient to noise, and because it was very efficient. In other words, the data was spread across the entire frequency band, so that now what happened is at the opposite end, as long as the signal was greater than all the combined noise within there, the data went through at a very, very fast data. To give you an idea, just as far as speed goes, frequency hopping, because it's not a very fast way to do it, caps out at about 1 to 1.5 megabits per second. It's about fast as you can do. Direct sequence, the first iteration of it went from 1 megabit per second up to 11 megabits per second, which, that was kind of the first generation of wireless LAN. What has dramatically folded forward is this terminology, and so everybody can, go home and impress everyone, is called OFDM. That stands for orthogonal frequency division multiplexing. Now, the idea behind this is that this really is the latest modulation technique. As a matter of fact, as the wireless LANs keep getting faster and faster and faster, what they're doing is essentially they're still using the same OFDM modulation. They're just giving it wider and wider channels. And we'll see the effect of that here in just a bit. Okay. The purpose, think of it this way. The easiest way to conceptualize what OFDM is that if we took the frequency hopper to where we had all that data broken up into small pieces, but instead of sending it on channels 1 and 8 and 2 and 3, essentially you take and you fire them all at the same time. Essentially there is a parallel data pass for all the technique. The idea behind this is that of that technology, some of those data points are actually used for data themselves, and other points within there are used for data correction. So it's a self-correcting or a forward error correcting modulation technique. The idea behind this is that instead of now knowing what order the hopping pattern came into, since we're essentially sending them all at one time, the only thing that's necessary to know was where's the starting point and where's the ending point. And therefore, that was originally worked best in what they call non-line of sight applications, to where it's inside of a city, to where you're reflecting the signal off of a bunch of buildings. Okay, what you're going to do is you're going to get differences in timing from each one of those. But as long, again, as we could get the starting point, we knew where the ending point was, this OFDM modulation would work. And it's worked very, very well. As a matter of fact, that is the latest technology that most wireless system is using. Okay. Now, one thing we need to get straightened out right from the very beginning is what we're talking about. No, we make products, we make 13 different radios covering the frequency bands from the 150 megahertz in the VHF frequency band all the way to 5.8 gigahertz in the SHF band, or the super high frequency band. All of those frequencies, no matter what they are, they're considered terrestrial frequencies. In other words, the antennas need to have a line of sight for when we're doing the design to get a reliable communication. They're not going to go through a mountain. They're not going to go through this, they're not going to go through the side of a hill. We need to understand that the antennas need to have a clear, open line of sight. So you'll hear that terminology again and again and again. And no matter which band we are, some of them are more tolerant to blockages within the line of sight between the antennas. But we'll cover what those actually mean here in the next section. Okay, so everything that we're talking about now, the bottom line is that the antennas can't see each other. We have to have a means of either going over whatever we're talking to or going around it. Okay. The next thing we need to get an understanding of is what is the difference here when we're talking about some of the characteristics from a transmitter and the receiver. Okay. You also may hear this term called a transceiver. Well, a transceiver means that a device has both a transmitter and a receiver in the same unit. It's really what it comes down to. We could spend days and days and days going through what a transmitter characteristics are, what are the receiver characteristics. What we need to be concerned with really is because we're moving data. We build data radios. We do not build audio radios. We're moving data from point A to point B. So we need to know how quickly can we move this data from here to there. So if we look at transmission time is primarily on this from the transmitter side controlled by two elements. The first one is how quickly from the time that we recognize we have data to send can we get that data up and running. That's what's known as the turn on time, or kind of an old radio term was what was known as the attack time. Okay. Once we are able to do that, we also need to look at how much bandwidth we have available to us. Think of bandwidth as kind of like, water pipe. Okay, if you have a foot wide water pipe, okay, you're going to be able to push through a tremendous amount of water. We neck that down to a 1/4-inch pipe. Okay, of course, we're going to be putting through smaller and smaller amounts. Bandwidth works the same way. So if we have, say, for example, on our narrowband radios, we have kilobits of bandwidth. When we get to the spread spectrum or the wideband, we have megabits of bandwidth. Okay. Now, there are also two terms when we're talking about a receiver that unfortunately get kind of sent back and forth, and that's the difference between sensitivity and squelch. Okay. What a sensitivity is the smallest amount of signal that the receiver can pick up to where it can actually pull the data off of it or demodulate that information off of that radio characteristic. Now, that receiver sensitivity may be incredibly small. Now, we need to understand that all electronic devices, or anything that actually has some current running through it, will generate a certain amount of noise. Okay, this combined noise of everything going on around us, and even the Earth itself radiates a certain amount of RF noise. Well, this combined noise essentially is what's called the background noise. Okay, well, the idea behind this is you may have a receiver sensitivity. You could design a receiver sensitivity very, very small, but the background noise may be greater than your receiver sensitivity. So what becomes important is how well can that radio distinguish between what is the incoming signal and what is the combined background noise. That's where the squelch comes in. Okay, what a squelch is what allows the radio to tell what is a valid signal coming into it versus what is just noise. Everybody's, I'm sure, has played with a CB or a voice radio at some point, and that squelch button you've actually touched, whether you believe it or not. You turn it down, there's nothing but static. You turn it up, and the only thing that comes across is other transmitters. Well, essentially, that's the same principle. We're doing this on the receiver side in the digital circuit. It is actually automatically converted in most of our radios. The receiver squelch is automatically adjusted. But when you're looking at specifications, you can't get necessarily tied up so much in necessarily the sensitivity, because those two actually work together. Now, when we're talking about bandwidth, this gives you an idea really what we're talking about as far as the differences here. So if we're talking about, say, a 1 megabit of throughput, okay, we compare that to an 11 megabit of throughput or a 72 megabit of throughput. Okay, what those do is those correspond with the different bandwidth selections that we'll see here in the coming days as far as what's available when we're setting up the radio. So if we can give the radio 20 or even 40 megabits of bandwidth, we're going to be able to push through a tremendous amount more information. Same thing as we cut this down to 10 or 5, that bandwidth, or the amount of data that we can push through there, is going to essentially suffer in the same way. Okay? We'll catch that in much more detail when we get into the radios, but this gives a kind of a visual overview of what we're referring to. Okay. Now, spread spectrum actually is available in many different frequency bands and many different types of technologies. We need to understand that it's primarily, especially in the US, allocated to really a couple different frequency bands. The first one is what most people understand it as, that is the unlicensed bands. Well, what that means is in the ISM band, or the Industrial, Scientific, and Medical band, there are two primary frequencies that people are familiar with. One in the 900 band from 902 to 928, and one in the 2.4 gigahertz band. There is also one in the uni band, or the unlicensed national information infrastructure band, from 5.15 to 5.825, and that breaks into 3 different bands, and we'll cover those in more detail in the future. The bottom line we need to understand is that there is no such thing as an unlicensed radio. The difference is who gets the license. On some transmitters, it's up to the individual to license it directly from the FCC. Okay, what that does is that essentially gets you private use of that frequency. In the unlicensed band, the 900.24 and 5.8 gigahertz band, we as the manufacturer actually get the FCC approval, not the user. So therefore, we have to sell the radios with very specific antenna types, cable links, connectors, so that everybody gets to play by the same rules. In other words, nobody gets to exceed how much power they put out that then will therefore travel that much further than anybody else. Okay? So a good exercise here is to take a look really at when we talk about the different frequency bands, some of the characteristics or the divine them from one to the next. These same characteristics could be, conversely put all the way from, say, 150 megahertz. The changes in between them or the differences between them can be seen all the way from 150 megahertz all the way to 6 gigahertz. Okay, so what I mean by that is what you're going to find is a key element is that the frequency of operation, this is the primary frequency that the transmitter is putting out, not how fast we're modulating the data on top of it, but this is the primary frequency. The lower in frequency you go, the more penetration that you will get through in vegetation and the closer it will follow to basically the earth. Okay, so what you'll find is that, say, 900 megahertz frequency compared to these other higher frequencies has basically a better penetration or can travel further than, say, a 5.8 gigahertz frequency can on the Earth's surface. Now, what is a little bit unique there is that you also will find that essentially the next section we're going to be covering is actually the antenna section. The actual antenna size is physically based upon the antenna or the frequency of operation. We'll come back to that in a minute. Okay, so as we compare this, the 900, the 2.4, the 4.9, and the 5.8, all of those are what's in that spread spectrum category. The 900 megahertz will actually travel the furthest of all of those, but as it would have it, it actually has the fewest number of channels or the narrower bandwidths. Okay, so unfortunately, that band has a certain limitations to how many different users could be on one individual frequency. The 2.4 is a little bit better on that, and it's not as good as going through trees or vegetation, but it is better at going through trees and vegetation than you get at the higher frequencies. Okay, so even if we compare that all the way back to 150 megahertz, the lowest frequency that we manufacture, that frequency is fantastic for going through vegetation, following the Earth's terrain. It goes a very long distance. So therefore, one of the things that the FCC recognizes is because it is traveling much further and there's higher output power available, they have an incredibly small bandwidth. In other words, you have to pick a very small slither of operating frequency so that you're not basically taking up the entire frequency band. So we're going to find that as a common characteristic that has anything to do with radio. If you're getting an advantage, you need to look for the disadvantage. In other words, to get something, you're giving something up. Okay, so one thing that you get in the 900 megahertz frequency band is it will travel quite well. The downfall to that is the fact that it has the fewest number of channels. So we look at, say, the 5.8 gigahertz band. It has the greatest number of channels. Okay, but it also means that you need to have a direct line of sight between the antennas because you'll get very little, if any, penetration through vegetation, which is, trees or the ground or anything like this. Okay, so it's always a balancing act. Okay, so as you see here, we have 3 unlicensed bands, the 900, the 2.4, and the 5.8. The 4.9 is actually a very unique frequency, which we'll cover when we get to the radios. That is actually a public safety band. It is licensable for municipal applications. Okay, so we'll come back to that and what the characteristics of that are here in a second. Because where I want to get to is I want to get to the antenna fundamentals. Because as I mentioned to you before, one of the key changes that we can make in any radio system is how we make an antenna and the cable that's attached to the antenna. They become primary elements of what makes the radio transmit. Once we see the numbers and how that actually works, it'll make a lot of sense. Okay? So the first thing we're going to do, let's go ahead and get the hard part out of the way. We need to look at the first thing that is a concern, which is the mathematical calculations called a decibel. Okay? Now, the only thing that we need to really be concerned about is we need to understand that dB is the short form of decibel, and it is a logarithmic number. In other words, once you get a gain of 2, really that corresponds to 3 dB. So in other words, a gain of 4 will give us 6 dB. So when the number doubles, it goes up by 3D, or gets cut in half, it goes down by 3D. So the key to understand here, the key number is 3 dB. The reason that we do this is because everything in this radio world deals with power increases or power losses. So we try to keep everything at this dB value as long as we possibly can, because essentially to multiply these linear numbers, these power scales up and down, we can just simply add or subtract these logarithmic numbers. Now, it may be a little, intimidating at this point, but it'll make a lot of sense. The easiest thing to keep in mind is the magic number here is 3 dB. So when we're talking about antenna gain, okay, what we're talking about here is that when we see a gain on an antenna, every time that you see the value of 3 dB, that means that power is doubling, okay? So if we've got a 6 dB gain, we're actually increasing the power times 2 for 3 dB, and then increasing it again for 4 times the output power. Okay, so we can see here that the numbers become very large very quickly. The idea behind this is that we need to be able to understand how much energy is being put into the air. Okay, because what we're trying to do is we need to know how much energy is being transmitted so that we know the losses over a distance, so that at the opposite side we know how much signal is arriving at that antenna, so that then we can make the calculations to figure out, do we have enough energy into the air to be able to make this wireless system work. The way that it does is this term called effective radiated power, or ERP. Okay, really what it is, it's a very simple calculation to where you take the output power of the radio, we add to that the gains of the antenna, and then we subtract the losses in the cable. That's going to tell us how much energy is going into the air. Then at the opposite side, we take the received signal into the radio, is the RF power in the air, the gains on the antenna again, and then the feed line losses will tell us how much energy is arriving at the opposite side. Now, what we're going to see here is that as an antenna increases in gain, we actually are making that antenna more directional. Now that may be absolutely abstract at this point, but you're going to have to bear with me because we need to understand one key thing about an antenna. It's a passive device. In other words, that antenna cannot make energy. It cannot increase energy. All it can do is manipulate the type of energy that it receives. So what's actually happening is that as we then are manipulating that signal, okay, so as we're changing the patterns of that signal, what we're doing is we're pushing it into different envelopes, okay? Let me give you an idea, because you're going to have to bear with me because I love drawing on the board. So what I'm going to do is I'm actually going to put up a blank screen here and see if I can kind of draw this a little bit on the screen to give you an idea of what I'm referring to. Okay, so let's go ahead and take an antenna. Okay, the way that this works really is what we're doing is we're actually creating out of both sides of this an electromagnetic wave. Okay, so we're basically going to have a similar pattern coming out the opposite side. Okay, So now what you do is that if you were to take a receiving antenna at a certain distance, what's going to happen is that's going to have a certain amount of energy. Well, what's actually happening is that you've got to understand that we're starting with a finite amount of energy. So as this energy goes out, essentially the walls or the amount of energy that is arriving at given points is smaller, or that's what's known as a spreading loss. Okay? So what's actually happening is that if you imagine this as basically a beach ball, okay? As the beach ball gets bigger and bigger and bigger, the walls on that beach ball are thinner and thinner, okay? So what we're seeing is that effect spread out over time. This is kind of the starting point of how we actually get gain, okay? We'll see that here in just a second, okay? So what we're going to do then is let's take a look at the two primary types of antennas, okay? If we were to break down antennas, we can really break it down into two main types, what we'll call both omnidirectional antennas and directional antennas. Now keep in mind, antenna theory, antenna design is its own four-year class. So we need to understand that we got to break this down into the smallest elements we possibly can. So the first thing is an omnidirectional antenna. And keep in mind, what we're looking at here is we're looking at the very top of the antenna. So we're looking from the sky down. And what this would do then is as the energy radiates, it radiates effectively out into a concentric circle pattern. Okay, so therefore, no matter where the receiving antenna is at the opposite side, you'll be able to pick it all up. Okay, so this is the type of antenna that we would use at a master or a repeater node, because this is actually where we need to be able to put an omnidirectional antenna. So if we're looking at the top-down view, and again, this is a very stylized drawing, so bear in mind it is nowhere near this perfect circle, okay? But that's as close as it's the best way to conceptualize this, okay? So now how do we make a gain on an omnidirectional antenna? Well, the easiest way to think of this is that what we're actually doing is we're taking that and we're manipulating that energy pattern and effectively compressing it from top to bottom, okay? So now if you were to take a look at, again, using our beach ball analogy, if you were to look at any one of these, let me get the pen here. If you were to look at the antenna being this far apart from this other antenna, you'll see here that the one that is compressed will actually have more energy at it than the smaller one, okay? So again, getting back to what we learned before is that to get something, we've got to give something up. So the way that we give this up on an antenna is effectively we're creating a point that now creates a point where the energy will be and where the energy will not be. What I mean by that is we create what's called this vertical beam width, okay? Now, the way that this works then, as we push this further and further out, the only downfall to this is that we need to understand that the locations that we are going to be putting out there need to fall within this vertical beam width. So this vertical beam width, let's say this vertical beam width is, say, 36 degrees, okay? Then that means that energy is effectively going to rise and fall 18 degrees. Okay, so if your receiving antenna is below this point, you can overshoot it. So you really don't want to necessarily get the highest gain omnidirectional you can find, or the highest gain directional, because the price that you're going to pay for that is this beam width. Okay, now keeping that in mind, what we can do is we can take a look at how this works really in a directional antenna. And again, this is my kind of stylized drawing, looking from the top down. A directional antenna, what it does is it compresses the energy in two planes, not only from the top to the bottom, but from the side to the side, okay? So if we were to look at the top of a directional antenna, and this is the most commonly used type of directional antenna, which is called a Yagi antenna. And we'll get to how that actually works here in a bit. Okay, so what this does is that now, looking from the top down, we're compressing that energy, okay? And then also From the side, we're compressing that energy. So now this not only has a vertical beam width, like we have in the omnidirectional antenna, but we also now have a horizontal beam width. So we need to make sure that the location that we're talking to falls within both the horizontal and the vertical beam widths. So this is the type of antenna that's going to be used for remote sites or going to be used in a point-to-point system. Okay? Now, in the exact same way that we found on the omnidirectional pattern, as the antenna increases in gain, then this energy keeps getting pushed into smaller and smaller beam widths. Okay, so the higher gain antenna that becomes, the more directional the antenna becomes. That's really where that terminology came from. Okay, now it's kind of a continuation of this thought. We need to take a look at polarization of an antenna. What I mean by that is essentially this is the antenna's reference to the Earth's surface, because everything that we're talking about here is going to be generally done on the Earth's surface. So what we need to look at is if you had two antennas, one that is perpendicular to the Earth's surface, this being the ground, okay? If we have this perpendicular to the Earth's surface, this is called a vertical polarization. If we were to take that same antenna and turn it to the side, that would be a horizontal polarization. Okay? Now, where this all comes from is that, you actually get a canceling effect between a vertically polarized antenna and a horizontally polarized antenna. Out in open air, in other words, out in a vacuum, out in space, these two would never see each other. Well, quite honestly, we're on the Earth's surface, so there's going to actually get quite a bit of reflections going back and forth the two. So what we're trying to do is minimize those losses. Okay, so what we do is we just want to make sure that all antennas have the same polarization. And because most systems are going to be a combination of both omni and directional antennas, we need to make sure everything is vertically polarized. It comes down to a very simple principle. If we horizontally polarize, okay, this being the top, if we horizontally polarize this antenna, is it a omnidirectional antenna anymore? No, it's actually a bidirectional antenna. Power goes this way and this way, but not over here and not over here. So this antenna type, its orientation to the Earth's surface is what makes it omnidirectional. Okay? All right. Now, the next thing we're going to take a look at is we use this term called feed line. And the reason we want to characterize this is the feed line is a specific tuned type of cable that allows us to efficiently move energy from the transmitter on the antenna with a minimal amount of loss to the antenna itself. Excuse me, from the transmitter, to the antenna. All right. So really what this is this is the pipeline for the RF energy from one radio to the next. Different cable types have different losses, and generally what you're going to find is that the lower in frequency band that you go, the lower the loss generally tends to be a more expensive cable, and also based upon the frequency and length of the cable itself. It's always expressed, the loss is always expressed in a certain dB by 100 feet or by meters. And that's actually done by the manufacturer themselves. They're the ones who are going to dictate this. Generally what you're going to find is, as a common element, is the higher in frequency you go, the more attenuation or the more loss you have in the system and the connectors and everything that's associated with it. So one thing that is common is it doesn't matter how much you pay for it, all feed lines and connectors will induce a certain amount of loss. No matter how well they are made, how well they're put together, anytime that you go into a coax, there'll always be a certain amount of loss. Well, let's go ahead and put some numbers to this, okay? The first thing is as I mentioned to you, this is a feed line attenuation by several different manufacturers and cable types. Okay, as you'll see here, this is a minus dB loss in 100 feet. Okay, let's go ahead and start with some simple numbers here. Let's go ahead and start with 150, excuse me, the 450 to 470. Okay, let's say we're using this RG8 cable. Okay, if we go ahead and look, that cable has effectively 3 dB of loss for every 100 feet. So what we learned about before is that The 3 dB loss, essentially we cut our power in half using 100 feet of cable at 450 megahertz. Okay, doesn't sound too bad. You can generally get that back as far as the gain of the antennas. But one thing that it does do is that if, as you see here, we increase in frequency, we then change from 3 to 4.5. So we're again cutting that power by not necessarily double, but close to that. If we then use that same cable at 2.4 gigahertz, we move from 3 to 7. Okay, so effectively what we're doing is that although that number may not seem the same, we're only getting a 4 difference, right? Really what the power level is we're cutting that power in half, and then we're cutting that power in half once again, and then in this case a little bit more. All right, so where most of the changes within a system can immediately be seen is that, let's say, for example, we're using a 2.4 gigahertz, say we have to run 100 feet of cable, all right? So the natural inclination, if you're running low on signal, is to increase the power, okay? Well, that makes a lot of sense, but if you think about this, if we were to double the output power on a radio, really what we're doing is we're increasing that output power by 3 dB. But as you see here, if we just choose a different cable type and say use a 1/2-inch HELAX at 2.4 gigahertz, we're actually gaining back over 4 dB. So we're actually getting a greater increase in the overall system performance by getting less loss in the cable than we actually do by doubling the output power of the radio. Once we get to the next section and take a look at the RF design itself, we'll see where these numbers actually come into play quite frequently. Okay. The one thing that is very difficult, or what happens to an antenna, we need to understand one key thing, is that if we have an antenna, and this is the receive side of the antenna, is that as this energy is coming towards this antenna, okay, if it strikes this antenna, that energy is not absorbed here. In other words, it doesn't suck it out of the air and push it towards the receiver. Okay? What actually happens is that energy continues on past. Well, what can happen is if we've got a surface, primarily metal is the worst thing, it'll actually reflect and actually go back towards the antenna. Well, what happens is that if these two waves arrive at this antenna and they're essentially out of phase, okay? See if I draw my phase right here, okay? They arise out of phase, they essentially cancel each other out. That's what's called a multipath, okay? Multipath is one of the largest killers as far as an RF system is designed. And we'll see, we will do everything that we can to prevent that, okay? Well, another phenomenon that occurs is that what happens is that phenomenon can actually happen within the antenna cable itself. Okay, that phenomenon is called a standing wave. Okay, the best analogy for it, bear with me because I love to go back to my whiteboard. The best way to conceptualize this is waves in water. That's really the best way to think of how a radio wave travels. Okay, so if we take and we have a very large pond, okay? Well, in the center of this pond, if we put a rock that is standing out of the water, well, if we stand on the edge here, okay, and we throw a rock in, what's going to happen is it's going to start making larger and larger waves until the point that it strikes this rock. Well, at that point, what it's going to do, it's going to start reflecting back. Well, as it reflects back, what happens is effectively these two waves meet and cancel each other out. That, for a lack of better way, is what's happening inside of the cable on a standing wave. So what we need to do is we need to minimize the number of these standing waves that we have within this thing. Because no matter how well or how good an antenna is designed, it will always induce a certain amount of loss. Okay, so what we're trying to do is there are a couple ways to look at this. There are different meters that measure this VSWR, or the maximum to minimum values in this standing wave pattern, essentially it's a mismatch in this impedance in cable will induce a standing wave. Okay, so again, anything that is reflected back from the antenna has the ability to essentially cancel out the outgoing power. So we need to minimize that. So what we're looking for really is, how do we actually measure that? Well, the best way as far as a field expedient, or a device that can be taken into the field and used at multiple different frequencies, is what's called a directional watt meter. Okay? Now, the key to the understanding this is that what a directional watt meter does, it allows you to measure the power going forward, and then it allows you to actually, this is actually a movable slug, you can actually take and look at the power coming back. Now, as kind of a general rule, the maximum you want to see here is 10%. If you see anything greater than 10%, then you have a problem somewhere in the cable or the antenna. It doesn't tell you where the problem is, but it does tell you that there is an issue between those two. So one way to actually do this is that if you have a high reflected power, in other words, if you're putting out 2 watts going forward and you have 2 watts reflected, you have a problem somewhere in the cable and antenna. Now, what that doesn't tell you is which is the problem, the cable or the antenna. Well, if you're to take this meter and you move it between the antenna and the cable, then essentially what you're doing is instead of being right next to the transmitter, okay, transmitter being here, if we move it up to this other end here, the way that you can look at it is, if you have a low power getting to it, in other words, no longer getting 2 watts, you're actually measuring, say, 0.25 watts up here, okay, then the problem is actually in the cable. If you are putting out the same power and the same reflected, the problem's in the antenna. So you can actually use this as a somewhat field expedient. And again, there are different ways to turn it on, and we'll see this when we get to the advanced section. In other words, depending upon the type of radio that we're using, there are different ways to turn the transmitter on. Okay, for example, the 192s and the 210s, there is a place in the advanced menu, or you can type in a radio on command for different radios. And we'll get to that when we actually get to the section as far as troubleshooting goes. Okay? To kind of finish this out, let's go ahead and look at some overall general block diagrams. Okay, the first one being the pieces and parts that generally go into a standard outdoor antenna mount, where you've got the radio itself here. Okay, the best way to think of it is, what inputs do we have to the radio? Well, we have the power input here. We have the device connecting to it, and that may be either serial or Ethernet, depending upon the device. And then we have the RF side of it. Okay, well, the RF side of it going forward, really what we need is, we need a device in there that, if we have a high amount of energy that comes into the antenna, we need to be able to take this to earth ground so that it will save the hardware that's connected to it. So what you have is the antenna, the coax here, the lightning suppression, and then a jumper cable that goes in there. And this is going to be common for just about any different antenna type or frequency or manufacturer. There's nothing that's unique to the way that we're doing it. The only thing that's any different when you go indoors or in a mobile environment, of course, the lightning suppression doesn't do you anything inside. If it's in a mobile environment, say for example in a vehicle, you've actually got the 4 best lightning arresters ever made in those rubber tires. Okay, so what it is depending upon the type of mount and how it goes together, is the type of interface and the type of equipment that you'll get. The only thing that's a little bit unique to this is the fact, and this is one of the main reasons that our Horizon series radios actually are designed to be mounted outdoors. Because again, most of the loss in the RF signal coming out of the antenna comes in this coax. So if we can eliminate it entirely by directly mounting the antennas to it, or minimize the amount of cable by integrating that in one of 2 different ways, either with an omnidirectional or directional antenna, then we can put most of the power out of that radio into the antenna to get the furthest distance out of it. Okay, there are a couple elements, and we'll cover this much more in detail in the future, but really what that is there are two things that of course, to get the benefit of having this mounted outdoor, we need to look at the downside. The 2 downside is, we need to deal with the weather, and we also need to put power to it. Well, it just so happened that we designed this at a very good time when something was coming out called Power over Ethernet, or PoE. Okay. Well, PoE actually provides both data and power on the same line. So what that did is that allowed us now to put in one single cable that provides both data and power to the radio. The radio actually has a separate, what we call a pole mounting kit. And we'll go into detail of how that's put together and all the pieces and parts to it. The bottom line is that once this is actually all put together, all the weatherproof plugs are on there, the solar panel on the front, excuse me, the solar cover, not the solar panel, the solar cover on the front, this becomes NEMA 4 rated, okay? So what this does is this allows us then to operate in an outdoor operation with a single or very simple solution as far as the installation goes. Okay? The last thing that we'll take a look at, really, this is kind of the odd characteristic, but as I mentioned to you before, what it is that there is a phenomenon that occurs in radio that essentially there are essentially null spots above and below antennas. And this really comes down to another characteristic, that if RF energy basically strikes a surface primarily of metal, that at a particular frequency or a particular wavelength, then what it will do is it essentially reflects off with almost the same amount of intensity it arrived at. Okay? To give you an idea of what I'm referring to that, and this is actually how directional antennas are made. Okay? The easiest way to think of this is what we're talking about here is we're talking about a sinusoidal wave or a sine wave. Okay? So essentially we've got our rise, we've got our trough down here. This complete revolution here is one wavelength. Okay, there's my lambda socks here, but okay. So if we look at one single wavelength, what are the highest points of intensity? Well, we've got the highest rise here, we've got the cross here where it goes back to the center, and we've got the lowest point here. Well, in this wave pattern, what does this represent? So this is 1/4 wavelength. Okay. This is a 3/4 of a wavelength. And that pattern will basically repeat every odd multiple of a 1/4 wavelength. So you'll see here that when effectively so the directional antenna that we've had before, the Yagi antenna, really it kind of works the same way. The antenna, let me draw one more little element here, it'll make a little more sense. So the energy is actually put into the antenna here, and what actually happens is that energy radiates out until it hits a point to where it reflects. That energy reflects back, then that energy reflects forward, and that energy reflects back until most of that energy goes out the front of that antenna. It uses the same principle that we talked about here. Okay? Again, what we're getting to is we're not trying to cover absolutely everything that you can possibly learn as far as wave theory, antenna design, everything here. We just want to get to a point to where we can utilize some of these tools that we've learned, because the next section we're going to be going into is the RF design. So we're going to get familiar with a few other terms that are used in that. But if we do need to space antennas apart, either vertically spaced, or if you're looking at the distance away from an antenna, you want to make sure that the reflection points here, okay, or these null points are at odd multiples of a 1/4 wavelength, and that can actually be measured at least in inches. What we're looking at is a 1/4 wavelength in inches is 2952 divided by the frequency in megahertz. So you can divide that into inches, feet, to give you an idea of what we're talking about. So a 1/4 wavelength at 900 megahertz is 3.2 inches. Okay. So the next section that we're going to take a look at is we're going to take a look at how do we apply some of this knowledge that we learned? How do we apply this theory and everything that we've started with? So in the next section, which is going to be the RF design, we're going to then add a few new terms, and we're going to start putting some of these numbers to paper. So it'll start making a little bit more sense as far as where it goes to. So if anybody's got any questions, I'll be happy to take those. I've been kind of following through there and hopefully adding the questions for the people that have been on here. But overall, it looks like we're doing pretty good so far. So what we'll do is we're going to go ahead and close this session down for the day, and we'll start again tomorrow on section 2 for RF design. Thank you very much.